It's the last part of the polynomials topic, basically. And the reason we didn't do it back when we were looking at polynomials is because I didn't think we knew enough functions, and it involves calculus. So now that we know more functions, how to differentiate and what have you, it becomes a little bit more relevant. So approximation solutions, because it'd be lovely if we could solve every equation, but reality is we can't. Some equations are just too difficult to solve, and an approximation sometimes will suffice. So we're going to look at two methods. The first one's a very basic idea, simply what we call halving the interval, and it works very nicely if the curve's continuous. So that's the key. The curve has to be continuous over a certain interval that we're investigating. So there's some random function. Let's say A is there and B is over there. So if I know the curve's continuous between A and B, and one of those function values is positive and one is negative, then somewhere in between it must cut the axis, so where it changes from positive to negative. And I guess the best approximation, if we had to, would be to average. In other words, halve the interval. So that's the idea. We just simply average A and B and say, well, this will be our approximation. Okay, so let's have a look at one. So we've got this quartic. Now it'd be great if we could factorise that, and yes, we could go and find solutions. But a bit difficult. Now they've given us a bit of a hint in that they've told us there is a solution somewhere between 1 and 3. We know there's a solution, and the reason we know that is because, well, it's a polynomial, so it is continuous. So there's my function. Function 1 turns out to be negative 16, and function 3 turns out to be positive 68. So we know a solution exists in between 1 and 3. So I'm going to guess that solution to be 2. Let's see how we went. No, that's not right. But now I can make my interval smaller. Because basically what we've now done, there's the 3 points we now have. Don't worry about the scale on the y-axis, I'm more interested in positive and negative. So originally we said at 1 it was negative, at 3 it was positive. So we've estimated the solution to be in the middle at 2. That turned out to be positive. But now I've got a smaller interval that I can trap the solution in. Because now I know, oh well, fair enough, but that now means the solution must be somewhere between 1 and 2. And I can halve the interval again. Yeah, all right. Well, let's halve that one. Let's try 1.5. And whoa, minus 10.9, so no. But again, I could do the same sort of idea and say, well, hang on. If 1.5 is negative, I now know the solution must be somewhere in between 1.5 and 2. So I'll average that. And I get 1.75. No good, negative 6.12. So let's try again. So now I know the solution must be somewhere in between 1.75 and 2. Now the question said, you remember, to 2 decimal places. So when I'm doing my average, I'm only doing that to 2 decimal places. So 1.88 would be to 2 decimal places. No? Okay. So we'll try again. So somewhere between 1.88 and 2. So again, average them round to 2 decimal places. 1.94. Oh, it's getting closer. Okay. But now I know the solution is somewhere in between 1.94 and 2. So we'll try 1.97. Oh, that's very close, isn't it? 0.001. Now remember, it's not the answer to 2 decimal places. Sure enough, the answer to 2 decimal places there is 0. It's what we're subbing in to 2 decimal places. So the answer is still not it's not 1.97, but I now know it's in between 1.97 and 1.94. If I average those, I get 1.96. So, oh, hang on, I'm on the other side, but further away. Okay, let's now try again. So I now know it's between 1.96 and 1.97. Well, hang on. Remember, we're doing this to 2 decimal places. So the answer must either be 1.96 and 1.97. The question is, is the solution going to be closer to 1.96 or 1.97? Don't let the y values deceive you, because you don't know what the curve's doing. It might do something silly and rise very rapidly. So temptations to say, oh, it'll be 1.97 because that's closer to 0, but that's not a valid explanation. What we basically do then is go to 1 decimal place more. And I want to see which side of 1.965 it lies on. And then that'll tell me which ones it's closer to, 1.96 or 1.97. Now, 1.965 turns out to be a negative number. So all right, as it turns out, it is closer to 1.97 than 1.96. So that's going to be my approximation, 1.97. This sort of approximation, I think, very tedious. But of course, in the day and age now where we have computers and spreadsheets, you can set up a formula very easily for something like this and do lots and lots of calculations very, very quickly. And in reality, that's what we do. In a test, they're not going to make you go all the way and do, all right, let's just go find the final one. They usually just say, look, just do one application and find a better solution or something like that. So 1.97 would be our approximation. So how many times did we halve the interval then? Anyone count them as we were going? It was... How many, sorry? 8. Okay, so 8 times it took us. And that was to 2 decimal places. Well, our friend Newton, who does so many things, because as I think I've said before, well, you know, they didn't have telly, so they had to do something. So they just played with their maths for entertainment. His method of approximation came up with a different idea. Okay. Now, in order for this approximation to work, it all relies on the very first approximation. The first approximation has to be a reasonably good approximation, because what it ends up doing is, at that approximation, we end up drawing in a tangent and find where the tangent cuts the axis. So there's random curve. Same, I wanted to find the solution on the left of x naught there. And so x naught is my approximation to that solution. So all right, I'll go down, draw in a tangent. Where it cuts the x-axis, that'll be my next approximation. Now, if I pick a good approximation, because of the curvature, that tangent should get closer to the intercept, and that's the idea behind it. So at x1, then I could draw another one, and so on. Now, of course, if we happen for a first approximation, pick a stationary point, we're in trouble. Because the tangent would be horizontal and it will never cut the x-axis. So that is what we technically call a woeful, no, it's not true. That's just a very bad approximation. We don't want the horizontal tangent. Using the tangent x naught, we find x1. Now, let's actually work out the equation of the tangent and find where it cuts. We know the slope of the tangent would be, I just need 2 points. Well, we've got 2 points, because we know x naught and its y value, function x naught, and the other one is the x-intercept, so x1, 0, so y2 minus y1 over, and so on. So we know the slope of the tangent. So the derivative we know is equal to the slope. So rather than finding the equation of the tangent, we'll say, well, hang on, I know the slope at x naught is f dash x naught. So it'll be equal to the slope of the tangent. And basically, we rearrange this formula to come up with the Newton's method. So just playing around with it. And so if our first approximation is good, then to find x1, remember it's x1 we're trying to find, that second approximation, everything there that has x naught in it we can work out. X naught's the first approximation, x naught is the y value, and f dash x naught is the slope of the tangent. So all those things can be calculated. So therefore we should be able to work out x1 using this simple little formula. No, we don't have to derive that formula every single time. We can just quote it and use it. So it'll be our first approximation, but what we'll do is we'll subtract this fraction. The fraction is the y value over the slope. Now how do we know if we've got it right? The slope has to go on the bottom. Remember how I said the horizontal one fails? That's why. Because the horizontal one would have a slope of 0, and you can't have 0 on the bottom of the fraction. So if ever you're unsure, which one goes on top, think of that. Slope can't equal 0, can't have 0 on the bottom of the fraction. I'm pretty sure that formula's on the resource sheet they give you in the exam anyway, if you do get caught up. And then you can keep going and keep going and keep going. So to generalise that formula, we could say, oh well, xn plus 1 is xn minus function xn over the derivative. Well, let's do that same question and see how much better it is. Right, pretend we don't know the solution. Okay, we came up with an approximation before. So I've got the function, I'm going to need the derivative for this method, so 4x cubed plus 2. Now I've got to think of a first approximation. They've told me it's between 1 and 3, they said, wasn't it? That was back in the first question. So I'll pick 1.5. I don't know why logically I didn't pick 2, but anyway. I'll pick 1.5 as my first approximation. So function 1.5, I'll also need the derivative. That turns out to be 15.5. Put it into our formula, and I get my next approximation is 2.21. So function 2.21, no. And f dash 2.21, sub it into the formula, and I get 2. So like I said, had I gone with the logical one, I could have already got to this one straight away. So 2, try again, function 2, there's the derivative, substitute, remember we don't know that's the answer yet. I wonder how this one will go. Oh, that's not bad. 0, 0, 1. And the slope of that point, 32.58. Think about what it's saying, by the way. The y value is 0.001, and at that point we've got something with a slope of 32, so it's quite steep. So logically we must be very close, you would think. And what do you know? x4 turns out to be, to 2 decimal places, 1.97. So we know, well, that's where we're going to stop now, because every time we put in 1.97 we're going to get 1.97. So we've found our approximation. So 1.97 would be a better approximation, and that one only took me 4 goes. Reality is, had I picked the sensible one, remember we said it was between 1 and 3, and the sensible first approximation would have been the average, I suppose, which would have been 2. I would have got it bang straight away with that one.
So,
yeah?
How many times do you have to do like solutions again?
Well, I say, in reality, you keep going until the solution repeats itself. And then you know, okay, I've found the solution. So once it starts generating the same number each time, you know that's got to be your approximation. That's in reality, in real life, what we would do. And again, a spreadsheet would lend itself very nicely to that. In an exam, they'll probably say, well, just use one application to find a better one. So they can see you know how to use the application. How about a question like this? We're going to find an approximation to the square root of 23. So in order to do that, we need to come up with a polynomial. Well, it doesn't have to be a polynomial, but logically that would be nice, where we know the solution is the square root of 23. Anyone think of an equation that has a solution of the square root of 23, and don't say x equals the square root of 23. That would be a bad one, because remember, we don't know what the square root of 23 is. That's what we're trying to find out. So the next best one would be, x squared equals 23. Well, we're making a polynomial, so x squared minus 23. Because essentially we're saying solve x squared minus 23 equals 0. We know that will give us the solution, the square root of 23. So that's going to be my function. My derivative will be 2x. I need a good first approximation. I know that the perfect squares, I've got 16 on the left hand side, which would be an answer of 4. I've got 25 on the right hand side, which would give me an answer of 5. Square root of 23, well, I think it's going to be closer to 5 than it is to 4. So I probably used 5, did I? Before I get to my approximation. Sometimes, rather than keeping on working out the derivative each time, we set up just a formula like this and just sub into the formula each time. It's just a matter of choice, how you want to do it. So this one I'm doing that way, where I'll just sub into the formula. My first, sure enough, yes, my first approximation is 5. So let's sub in, and I get 4.8. It must have been 4.80 because it says 2 decimal places. So 4.8, sub it in again, x2, 4.7955833333, which again is 4.8, isn't it? But we want 2 decimal places. What's 2 decimal places? That is 4.8. Oh, maybe we found it. So there you go, 4.80, we found it straight away. Some problems though. Some problems we need to be aware of. If we pick one and it ends up getting an oscillation, now what do I mean by that? There's random curve. Say I want to find the solution there on the left hand side, the left hand one. So I want to find that one. And I pick x1. So there we go, tangent comes in and we get x2. Unfortunately, I've happened to pick the spot that when I now draw a new tangent in, it goes back to x1. So x1 will produce x2, x2 will produce x1, x1, and it'll just go around and around and around and around. That was just a really unfortunate choice for x1. I happened to pick that particular spot. So that's something that might happen. It would be very rare, incredibly unlucky, but it could happen. Now, if you picked a point that was on the wrong side of, say, the stationary point there, remember, I want to find the one on the left-hand side. So if I wanted to find the one on the left-hand side, and I picked a point where the tangent's on the other side of the stationary point, it's going to approximate the wrong solution. Because it's going to go, it'll get me a solution, but not the one I'm looking for. So that could be a problem as well. So there we go. Couple of questions playing with approximations.